Okay, so I'm going to start off from the end of lecture 2, and this will be the recording for lecture 3, which is going to be on Tuesday, September 2nd. But let me touch on a few things from lecture 2. So in lecture 2, we talked about modeling and the Laplace transform. So in particular, I'm going to just highlight a few things from the Laplace transform. Okay, so in the Laplace transform, we're interested in converting differential equations to the Laplace domain in order to combine different differential equations and use block diagrams. And ultimately, we want to design controllers, and we're going to use the frequency domain to design our controller. So we want to get comfortable going back and forth between the time domain and the frequency domain. So I'm not sure why this isn't loading, but we have the definition of a Laplace transform, and maybe I'll just pull it up on the regular slides here. So basically, we're taking the integral of our function multiplied by this exponential and integrating over time. Not sure why this isn't loading. So let me try to reload this. Okay, in any case, I have them right here. So the example here is that we have this exponential function, a some gain times the e to the negative alpha t times our unit step function. So when we plot this, it looks like this image on the right, where we have this exponentially decaying function for all time greater than 0, and the unit step gives us 0 for any time less than 0. And we're going to show that our Laplace transform gives us this function. So let me go to the notes here. So I think we would have had time to do this in class, but just so we're all on the same page, I'll go ahead and do that here. Give me 1 second. All right, so we're going to start by taking the Laplace transform of f of t. So we take the Laplace transform of f of t, which gives us our f of s. Okay. So the Laplace transform of f of t is the integral from 0 to infinity of our function, a to the e negative alpha t times the unit step. And so the unit step really is defining this bound from 0 to infinity. So we can ultimately know that that's baked in here to the integral. And so this is being multiplied now by our e to the negative st dt. So this is applying the Laplace transform to this function here. Okay, and so what we see now is we can actually combine these two exponentials. So we get our integral times a e to the negative alpha plus s times t. So when we are multiplying two exponentials, we can add their exponents. And so that's what I did on the top here. And I did an extra step where I factored out this negative sign. Okay, so now we're ready to take the integral of this guy. And so the integral of an exponential is just the exponential divided by this. So we have a divided by negative alpha plus s times our exponential. And then we have our what we're going to substitute in for t here. So this is really this is t is equal to infinity and t is equal to 0. Okay, so if we plug that in, let's work on doing that. So we're gonna apply this to t. So we have infinity minus e to the negative alpha plus s times 0. So really we can't plug in this infinity, but we're going to take the limit as t goes to infinity of e to the negative alpha plus s times t minus e to the negative alpha plus s times 0. Okay, so anything times 0 is 1, or sorry, any exponential to the 0 power is 1, so this goes to 1. And now as we go towards infinity, as long as alpha plus s is greater than 0, then this guy is going to be a decaying exponential. So it looks something like this. And so as time goes to infinity here, this is our e to the negative alpha plus s. This will go to 0. So ultimately this goes to 0 and this goes to 1, as long as this holds true. So what do we have left? We have a divided by negative alpha plus s times negative 1, right? Because we have this negative sign here. Okay, so this gives us a over alpha plus s, which is our f of s. All right, so that's how we get the Laplace transform. Now, there are several other examples, and I won't go through them all, but you're welcome to go through the slides on your own, and you'll see the exact steps laid out for you for the unit step, for this function here that I made up, which is a delayed version of the unit step minus the unit step times 3. There's the impulse function, the sine and cosine. There's also exponential sine and cosine. So all of these are here, and I do encourage you to refresh your memory on how we got these, but there is a very handy transform table that you can find on Canvas. And so, for example, like this function has its transform pair here. defined. And so this is going to be very handy for you when you're working on the homework and also on the exams. You don't need to necessarily compute the Laplace transform from scratch. However, it is helpful to know where this is coming from. And there's a few properties that I want to point out. So the first property, let's see, is linearity. So it turns out that the Laplace transform is actually a linear function. And so what that means is that Laplace transform satisfies both homogeneity and additivity. And you can see the proof below here. So really what this boils down to is if you scale the function in time, you're going to scale it by the same amount in the Laplace domain. And if you add two functions in time, you're going to find that their functions in the Laplace domain also add. Okay, the next example is this time shift property. So if you shift a function in time, this is like multiplying by an exponential in the Laplace domain. And if you shift in the Laplace domain, then this is like multiplying by an exponential in the time domain. So again, the proof is below, but just know that this is going to appear on your transform property table. Another property is integration. So whenever you have an integral with zero initial conditions, you're going to get this 1 over s appearing in the Laplace domain. And this is especially useful for things like capacitance. And similarly with differentiation, so instead of 1 over s, we're going to get s times our Laplace transform and minus any initial conditions. So usually we're going to almost always consider initial conditions to be 0 unless otherwise stated. And we will see an example of that here, but just know that a differential will mean S in the Laplace domain. So when we're going back and forth from differential equations to the Laplace domain, you'll see this property used a lot. Okay, and the proof is again below. It uses integration by parts. There's a couple of functions that are really interesting that are time dependent. So if you have just a function that is dependent on the time t, this is going to turn out to be 1 over s squared in the Laplace domain. And similarly, if you have a decaying exponential multiplied by time, this is going to be also a quadratic function in the Laplace domain. So kind of interesting there. So we're starting to see where this second order system is going to come in play, and we're going to focus a lot on the second order system in the second unit. I'm going to skip past this, but these are some more transform pairs. Okay, and this is where we're going to start back in the OneNote. So let me skip down here. So let's suppose that you're given the following function. F of t is equal to e to the negative t plus 3 times e to the negative 6 t. So the question is, how do you find the Laplace transform of this function? Well, we can actually use the property of linearity, right? So we can take the Laplace transform of e to the negative t and add it with the Laplace transform of 3e to the negative 6t. So if we do that, and if you go back to that first property we discussed, this first transform pair that we discussed back here, the exponential, right, is defined by this gain over alpha plus s. So here we don't have a gain, it's just e to the negative t. So our alpha is 1, and a is 1. So in our example, we're going to have this is 1 over s plus 1. And similarly, this is 3 over 6 plus s. Okay, so we can add these together, and this gives us our f of s. Now, suppose that we're given f of s is equal to 4s plus 9 divided by s squared plus 7s plus 6. This is often what we're going to see when we're working with these different systems. They're going to be combining different components together to give us this transfer function. And so the question is, okay, suppose that this is your, this is your input-output relationship. We're going to talk more about this in the transfer function lecture. But if this is your input-output relationship and you want to look at your output in the time domain, then we need to take the inverse Laplace transform of this. So something like this. But the thing is, taking the inverse Laplace transform of this guy is, we don't have a transform pair on our table for this. So how are we going to do this? I'm going to let you think about it for a second. So the answer is using partial fraction expansion. So you may have learned this once or twice before in another class, and we're going to see it again here in this class. So partial fraction expansion is going to be a great tool for us to take the inverse Laplace transform of this function to get it back into the time domain. This is ultimately how we're going to analyze systems. So this is key for analysis. All right, so to start, we're going to assume that f of s can be written as a over, so if we factor this on the bottom, we have s plus 1 times s plus 6 over 4s plus 9. So we can begin to write our partial fraction expansion as some term a divided by s plus 1 plus some term b over s plus 6. So having these in the denominator is helpful because we know how to take their inverse Laplace transforms. Okay, so the question is, what is a, how do we get a and b? Okay, so this is the partial fraction expansion method. So a is equal to our f of s times s plus 1, substituting in s equal to negative 1. Okay, so we have 4s plus 9 divided by s plus 1, s plus 6. This is our f of s. And then we're going to multiply it by s plus 1 and substitute in s is equal to negative. Okay, so when we do this, let me change colors. Hopefully, there we go. So this s plus 1 is going to cancel with this s plus 1. And so we're left with 4 times negative 1 plus 9 divided by negative 1 plus 6. And so this gives us 5 on the top and 5 on the bottom. So this gives us 1. Okay. Now we're going to solve for b. b is f of s times s plus 6 at s equals negative 6. So again, we're going to rewrite our f of s, which is 4s plus 9 divided by s plus 1, make this bigger, times s plus 6. And then we multiply s plus 6 on the top, and then we substitute it in for s is equal to negative 6. Okay, so again, we see that s plus 6 cancels on the top and the bottom, and we're left with 4 times negative 6 plus 9 divided by negative 6 plus 1. Okay, and so 4 times negative 6 is negative 24 plus 9, and this is negative 5. So negative 24 plus 9 is negative 15, and so negative 15 divided by negative 5 is 3. Okay, so what did we get here? So our new factored f of s is a is 1 divided by s plus 1 plus b is 3 divided by s plus 6. And so we can easily now take the inverse Laplace transform of this because of the property of linearity. So again, we can take the inverse Laplace transform of this guy and add the inverse Laplace transform of this guy. And so this gives us e to the negative t, and this gives us our 3e to the negative 6t. So this is actually the same f of t we had in the previous example. So this is how you would do the partial fraction expansion. Now, there is a special case where you're going to want to be extra careful. And so let me talk about that. But first, I want to mention one more property, okay, and that is the higher order differentiation. So we said that taking the derivative, the Laplace transform of a derivative of function gives us this s term. If we repeat that for higher derivatives, like the second order, we see that we have s squared times our f of s minus s times any initial conditions minus the derivative of f at any initial conditions. So when we assume that all the initial conditions are 0, we're left with just this first term. And so we see that for higher order terms as well. All right, so let's go now to our final example in lecture 2, and then we'll move on to lecture 3. Okay, so the question asks us to find the solution to this differential equation, our solution being the position of this mass in the mass spring damper. And we're given the initial condition that the position is initially at 0 and the velocity of the mass is initially at 1. And we're told that there's an upward force of this exponential term, e to the negative 2t. Okay, and ultimately we want to find x of t, our solution. But in order to do that, we need to first find the transfer function. Okay. So let's start by taking the Laplace transform of excuse me, our differential equation. By the way, this dot here and this double dot, this means the second derivative, and this single dot means the first derivative. So again, we're inherently implying that this x here is a function of t. We just simplify the notation and just write x, but inherently it is a function of time. So that's why we're taking the second derivative and the first derivative with respect to time. Okay, so if we take the Laplace transform of the second derivative, so this is s squared times x of s minus our initial condition. So let's go back to this, minus s times f of 0. So s times our x of 0, because our function is x here. And so x of 0 is 0. So this goes to 0. Minus our, if we go back to this, minus the initial condition of the derivative. Okay, so that's where this guy is going to come in. So the initial condition of the derivative is 1. Okay, so that's the Laplace transform of this guy. So again, we're using that property of linearity. Maybe I can go back here a step. Okay, if I move this down here a second. So ultimately what we're doing is we're taking the Laplace transform of x double dot and adding it with the Laplace transform of 2x dot plus the Laplace transform of x plus the Laplace transform of e to the negative 2t. Okay, so all we did so far is the Laplace transform of the second derivative. Now we're going to take the Laplace transform of the first derivative. So if we go back, our first derivative is s times our function x minus any initial conditions. So again, this initial condition is 0, so it's going to be plus s times x of s. Okay, the Laplace transform of x is x of s. And this is equal to the Laplace transform of e to the negative 2t, which is just 1 over s plus 2. Okay, so what are we left with? We have s squared times x of s minus 1 plus s times x of s plus x of s is equal to 1 over s plus 2. All right, so now we are going to highlight our x of s terms and try to isolate everything on this side. So we're going to have s squared plus s plus 1 times x of s, and we're going to move this negative 1 to the other side, so we have 1 plus 1 over s plus 2. Okay, and if we find a common denominator, then we have s plus 2 plus 1 over s plus 2. So 1 is like s plus 2 divided by s plus 2. This gives you 1. So we just found a common denominator. Now we can add the numerators. Okay, so we have s plus 3 divided by s plus 2 is equal to s squared plus s plus 1 times x of s. So our x of s is really s plus 3 divided by s plus 2 divided by s squared plus s plus 1. This is our x of s, which is good because we want to find x of t. So to find x of t now, we're going to take the inverse Laplace transform. Okay, but taking the inverse Laplace transform of this guy is not so straightforward. So we need that partial fraction expansion again. So let me walk you through this. So now we have x of s is equal to s plus 3 divided by s plus 2 times s plus 1. Oh, and let's see. It seems I forgot something here. All right. So back here, I had a 2 times the derivative of x, and so I forgot we need a 2 here. Okay, so I'm just going to fix that everywhere. So this will allow us now to factor this term. So this is s squared plus 2s plus 1 is s plus 1 squared. Okay, so hopefully that wasn't too confusing, but all I did was I just forgot this term 2 here. Okay, so now you'll notice that we have this repeated roots term, and this is always, we have to take an extra step in our partial fraction expansion whenever we have repeated roots. Okay, so we start by finding a, which is going to be s plus 1, let's call it, and b is going to be our s plus 1 squared term, and c is s plus 2. So this is now how we're going to factor our x of s. So we need this extra term here because of this repeated roots. Okay, so the highest order terms, b and c, can be found with this same formula we had before, this residual formula where we took x of s, multiplied it by our denominator at that term, and then plugged in for s equal to -1. So I'm not going to go through all of the math here, but it turns out that this is going to be equal to 2. And then for c, we have our x of s, this guy, times s plus 2 at s equal to -2. And this is going to turn out to be 1. So you can go through the math on your own, but for the sake of time, I'm going to skip it. So now the question is, how do we get a? So the easiest way to get a is to actually plug in now b and c, and we can solve for a. So we have one unknown and one equation. So this is our left-hand side, s plus 3 divided by s plus 2 times s plus 1 squared is equal to a divided by s plus 1 plus 2, because b is 2, divided by s plus 1 squared plus 1 divided by s plus 2, since c is equal to 1. Okay, so in order to continue, we need to find a common denominator on the right-hand side here. So our common denominator is going to be s plus 1 squared times s plus 2. So in order to get this common denominator for A, we need to multiply by s plus 1 times s plus 2. For B, we need to multiply by s plus 2. And for C, which is 1, we need to multiply by s plus 1 squared. So this will give us our common denominator. And then all we have to do is equate the numerators. Okay, so there are many steps in the algebra to do this. I'm going to skip past this. So if you follow from this slide here on down, you'll see the steps. So we got to this point here. And so you just continue to multiply all this out, and then you're left with the following. So you're going to equate s plus 3 with this top term here. Now the key is to equate the terms. So for instance, we have a single s here, and so you'll count, okay, we have a, so we have s is equal to a times 3s, and then we have a 2s, and we have a 2s, right? And so all the s terms should be equal to the s terms on the other side, and so now we can solve for a. Excuse me. So we have 1 is equal to, so we can divide by s first of all on both sides. So we get a 1 is equal to 3a plus 4. And so 3a is equal to -3, and so a is equal to -1. Okay, and that's what we got here. You could also pick the s squared terms. You could pick the s to the 0 term. It doesn't really matter, but you'll get the same answer in the end. So now we can plug in our a into our factored term here, and then we can take the Laplace transform, inverse Laplace transform, excuse me, of each of these terms. So the inverse Laplace transform is this guy, and the inverse Laplace transform is this guy. So notice there's this extra t now here, and then the inverse Laplace transform is this guy. Okay, so this is the solution, which is the position of our mass, right? So this mass is oscillating up and down, and it's going to be oscillating according to this function, and eventually it will be damped, but this forcing term here is what's driving this oscillation. Okay, so that's the solution to this problem with using the partial fraction expansion in the case of repeated roots. Okay, so just a reminder, homework 1 is due Tuesday, September 2nd, along with the 2 on-ramp tutorials, and you'll need to upload your certificates to Canvas. Okay, so let's move to lecture 3. So lecture 3 is all about linearization. So what do I mean by linearization? Well, remember we said that a linear system must satisfy 2 properties, additivity and homogeneity. So let me go into slideshow mode before I forget. So if we have these 2 input-output if we have these 2 inputs and 2 outputs, then adding the inputs will result in adding the outputs. That's what additivity means. And homogeneity means if we scale the input, then we have to scale the output by the exact same amount. So it's linear only if it satisfies property 1 and property 2. All right, so now we're going to check if the following function is linear. So we did this in the first lecture, but let's see. We can go to lecture 3. All right, so let's check if the following function is linear. So how do we start? Give me 1 second. Okay. Okay, I'm ready. All right, so we start by checking either additivity or homogeneity, right? So if we have x, why is it? If we have x1, yes, x1 plus, say, our x2 input, and we apply the function, what do we get? Well, we start with our input, which is x1 plus x2. Then we apply the function, which is squaring the input. And so this gives us x1 squared plus 2x1 x2 plus x2 squared. Okay, now let's check if we apply the function to the first input and apply the function to the second input and add their result, do we get the same thing? Okay, so this guy is going to be our x1 squared, and this guy is x2 squared. So if we add them together, we get x1 squared plus x2 squared, which is clearly not equal to the function applied to their added inputs. Okay, so right off the bat, it does not satisfy additivity, and I can bet that it's not going to satisfy homogeneity either, but let's just check. So if we apply the function and we scale the input, does this equal the scaled version of the function? That is the question. So let's scale the input and apply the function. So our input is alpha times x. If we apply the function, we're squaring the input. So this is equal to alpha squared times x squared. Now, if we scale the output after applying the function, so our input is x, we apply the function, and then we scale it, this is clearly not equal to first scaling the input and then applying the function. Okay, so again, neither additivity or homogeneity is satisfied, so this is a nonlinear system. Okay, let's check if the cosine function is linear. So a similar way, now our input is t.